Welcome back to Common Core 1.2 Part G. Well, it's the last part of this section. Time for a happy dance. So, the next thing we're going to cover is how to turn a negative power into a fraction. So 6 to the first just means 6, because it means 1/6. Well, okay. But if I have 6 to the negative first, negative member means 1 over, so it goes from top to the bottom. So if 6 times is big, 6 times is small. It means 1/6 the size. In that same way, where 6 square means 6 times 6, or 36 times as big, 6 to the negative second would be 1/6 times 1/6, or 1 over 36, 36 times as small. So basically, a negative just means 1 over. So 3 to the negative second means 1 over 3 squared. 4 to the negative fourth means 1 over 4 to the fourth, and so on. You try. Go ahead. Hopefully you have 1 over 7 squared. I don't need 1 over 49 here. If you have it, that's wonderful, but 1 over 7 squared is certainly where I'm fine too. And 1 over 3 to the fourth. Again, if you have 1 over 81, cool, very cool. Skills practice time. Again, all I need is 1 over. Go ahead. Let's see how you did. 1 over 9 squared, 1 over 2 to the fifth. Now, before I go on scientific notation, I may in class break and go further with this section, this idea, but for just the video, I just want to give you the basics. Now, the last thing is scientific notation. Scientific notation is a system to measure extreme numbers, such as, well, the extremely large, such as large numbers of people in a crowd, or extremely large, the universe, or even larger, the national debt. But that's an argument for another time. So, or the extremely small, bacteria, maybe a flea, or the atom. But mostly the extremely large national debt. But the easiest way to do this scientific notation is to start with a 1.0. In other words, the number 1. But the decimal goes between the 1.0. And the idea is 10 to the first power means I move it 1 space to the right, because it makes the number larger. So again, if I have 1.0 here, and it says to the first power, you'd move it 1 space to the right and simply get 10. So 1.0, 1 space to the right, is 10. Another example, 10 to the third. So don't start with 10. Start with 1.0 and go 1, 2, 3 spaces, and you have 1,000. Now, some of you are going to say, well, just whatever the number is, that's how many zeros. Not always. Just get in the habit of making these little, call them bumps or clouds or whatever you want. Just move 3 spaces or what have you. So start at 1.0, 3 spaces to the right. Now, why to the right? Because it's a positive exponent. So by moving the bubbles or clouds to the right, it's going to make the number larger. One more, 10 to the fifth. Well, you have 1.0 and 1, 2, 3, 4, 5. So 5 bumps to the right. Just please put a comma after every 3 numbers. It makes it a lot easier for me to read. The one exception is 10 to the 0. Start at 1.0. 0 means I'm not moving at all, which is why it's still just going to be a 1. Now the reverse is true as well for negatives. So if I have 1.0, when I have a negative, instead of going to the right, I'm simply going to the left. That's all. So you take 1.0, and if I have negative 1, go 1 to the left. So it's 0.1. By the way, 0.1 is fine, or 0.10 is perfectly fine. Either one I'm happy to accept. Take a look at a few more. 10 to the negative 3. Start at 1.0. 1, 2, 3. In the empty spot you put zeros. I don't care if you have 0.001 or 0.0010. Both are fine. Fill the gaps with zeros. Take a look at this one. 1, 2, 3, 4, 5. And you're going to have 4 zeros. That's why you don't count how many zeros, because when you do negative, it doesn't work that way all the time. Now the next part looks like this. So you have 1.24 times 10 to the third. We'll start with the given 1.24. Positive, so you go to the right. 1, 2, 3. Only one empty space. See, now if you try to add 3 zeros to this, it wouldn't work out. So now you have 1,240. So 1.24, 3 to the right, 1, 2, 3, 1,240. And the reverse, take the 1.24 here. Since it's negative, it goes to the left. 1, 2, 3, put the dot. Add the correct number of zeros where there's empty spaces. And what you'll find is 0.00124. We can also try the reverse. We can roll up the number into a scientific notation. So 123,045,000. What you do is take the first two numbers and put a dot there first, provided the first number isn't a 0. So the dot would go here, right between the first two numbers. And then you're going to count how many bubbles you need to get to the last one on the side here. So, okay, to go from here to here, I'm counting, well, let's see, 8 bumps, or 8 bubbles. So, 1.23045. If you put 000 or not, that's up to you. When you end with zeros, you can get rid of them or not after you put the decimal. You don't have to. That's kind of the point of doing scientific notation. Anyway, 8 bumps, put the dot, times 10 to the 8th. The reverse is true as well. To go from here, where do I need to go between the first two numbers that doesn't lead with the 0? To go from here to here. 1, 2, 3 bumps. Since this number was less than 1, when I put the 10 to the third, I'm going to put 10 to the negative third because it was extremely small, not extremely large. So you move it 3 bumps. 3.0, 3.23065 times 10 to the negative third. If you have the 3 zeros after, you can. But again, the whole point of this is to where you don't have to add those extra zeros. Now, all you know this side is why you need this stuff. Good question. Here's an example. As I'm sure we have already talked about, Earth is 93 million miles from the Sun. We've talked about that. So 93 million. That's a lot. That's right every time, 93 million. So just take between the 9 and 3. So you have 9.3. And how many bumps to get from here all the way to the end? I'm counting 7. So times 10 to the 7th. And that's a lot easier to write than the whole thing. So 9.3 times 10 to the 7th. So you understand anything between 10 million and 99 million will have a 7 in the exponential spot. So when I look at numbers, I can just look at this and get an idea of how big we're talking about. So anything to the 7 means like, okay, that's between 10 million and 99 million. And now let me take the dwarf planet Pluto, because on August 24th, 2006, Pluto got demoted. Except in Illinois. I think Illinois is holding out. Everyone else says that now it's a minor planet, not a planet no more. Anyway, the dwarf planet Pluto happens to be 3.67 billion miles from the Sun. That'd be a lot of zeros to write. If written out, it would look like this. But what we're going to do is put a dot between the first two numbers, provided the first number is not a 0. So 3.67. Just count how many bumps. Well, here's a trick, by the way. If you go from this way, you can count 3, 6, 7, 8, 9. Might be easier than trying to count this way, because you can just count by threes. I'm getting 9, so 3.67 times 10 to the 9th. Now, why is it positive? Because it was a huge number. It's not a small number. It's a huge number. So, put in scientific notation, looks like this. So I know 9 bubbles is between 1 to 9.99999 billion. So while 7s we're dealing with 10 million to 99 million, this is dealing with 1 to 9 billion. So clearly, look at the exponent number. Clearly, the dwarf planet Pluto is much farther away because 9 is bigger than 7. That's all I got to look at. 9 to 7 is going to be anywhere between 10 and 100 times larger. Now, our final example, our closest star to our Sun, Alpha Centauri. Alpha Centauri is approximately, let's see, millions, billion, 25 trillion, 260 billion, 733 million, 353,600 miles away. That's pretty far. Why, that's almost a mile for every dollar in debt we are. Anyway, right around the corner. So, here's how we do this one. Just put a dot between the first two numbers, provided the first number is not a 0. So 2.52607333536 times 10 to the 13, with the 13 dealing with 10 trillion to 99 trillion. By the way, comparing the Earth and Alpha Centauri, if Earth is 9.3 times 10 to the 7, and Alpha Centauri is 2.5 times 10 to the 13, if I took 13 minus 7, you get 10 to the 6th. 10 to the 6th is a million, and this is the gravity of what we're talking about. So Alpha Centauri is about 1,000,000 times farther away than Earth is to the Sun. So we might need a lot larger rocket to get to Alpha Centauri. So the next time someone asks you why we haven't gone to other stars yet, there lies the problem. And scientific notation helps us understand it. Will you need to know scientific notation every moment of your life? I don't know. But for those who are going to be in engineering or the sciences, it's a very valuable tool. We'll be doing a lot more of this in class tomorrow. Thanks again. Bye. Still here, huh? Well, you'll be sorry. This is your national debt, $19.4 trillion. That means every single American owes $59,890. And for actual taxpayers, the ones who actually pay into the system, is $162,000 per person. Why is that? We spend nearly $4 trillion a year in spending and only make about $3 trillion. And to be honest, I'm not even too sure about these numbers, because that only comes up with $0.5 trillion, and we've gone $10 trillion more in debt than we did about 7-8 years ago. So you figure that out. Well, anyway, happy indentured servitude.